Okay, so let's continue. Well, in this video, we are going to talk about one big problem with the K-means. Okay, we are going to load a new dataset, and it is called A2 dataset. And this dataset is quite common in the research world, and we are trying to, excuse me, this is the dataset we use to evaluate the clustering algorithms. Okay, so if you load this set, you will see there are just two features, X and Y. And if you want to plot that, then you can see there are really a lot of the clusters. Okay, so well, and you can see if you see the range of the x-axis and the y-axis, and they are not quite the same. So we want to do the standard scalar, and after that, we know there are a total of 35 clusters. So we have already known that. So we do the k-means, and then we want to cluster the k-means, the samples into 35 clusters. Okay, and after that, this is my result. I visualize the clusters with different colors, and also I visualize the centroids. Okay, so in this result, do you see any problem? Okay, take a look. Okay, so what I can see is here. So in the very center, well, there is one cluster. Somehow it receives two centroids. So there are two centroids. Divide one cluster. And then here, there is only one centroid right between two original clusters. So we cheated, and we know there are a total of 35 clusters. However, even when we cheated, it's not guaranteed that for each of the cluster it can have at least one centroid. So remember at the very beginning when we talk about the k-means in the last lecture, we say for the majority of the samples in one cluster, well, eventually that cluster will drag one centroid to the middle, right? So that is the reason we started from the centroids at the random location. We don't worry about that too much, because later we are relying on the majority of the samples in a cluster to drag one of the centroids in the middle of that cluster. However, well, when there are so many clusters, well, this is not that reliable. So here, well, there are two centroids sharing one cluster, and then here two clusters sharing only one centroid. Okay, so in the next part is, I want to emphasize that finding the optimal solution of the k-means is NP hard, which is, well, you can't do this in polynomial time. So in this case, it is not a perfect result. And how do we find the perfect clustering which can cluster 35 of the centroid in the at the right locations? The answer is we don't have that. Okay, and the running time of the k-means is the OMD MKDI, and the M is the number of the samples, and then D is the dimension of the vector. So how many features do you have? And the K will be the how many clusters you are trying to cluster the samples into, and then I is the number of the iterations needed. Okay, so for this I, and well, remember in the for the k-means, we say that is an iterative process because we have to assign all the samples to the nearest centroid, and then we are going to recalculate the location of the centroids. So this is an iterative round, and in reality, well, this I is usually a very small number. You don't have to worry that you have to run 1,000 rounds before it converges. It usually converges much faster than that. So, well, usually we say it is a linear algorithm because m is the only large number. K Well, how many clusters? That's usually a very small number. And for the D, the number of the dimensions or the number of the features compared with the number of the samples. The number of the features is usually a very small number too. And then for the I, we have said, well, the K means is a algorithm convert very fast. So, well, usually we say the K means is a linear algorithm, linear to the number of the samples. Okay, so the next question is, what if the m is a very large value? So a lot of algorithms struggle a lot with a very large data set, and well, K-means is doing okay with the larger data set. And for example, well, 1 week ago we talked about the SVM, for example, and SVM is a algorithm struggles a lot with the large data set. So even though we know K-means it does okay with large data set, if the data set is very large, and one of the strategy we can still do is we can well, sample part of the data for clustering instead of using all the data for the clustering. Okay, so the next one is a very interesting question. So what if you have a dataset with a mixed value of the attributes, height and well, height and the weight, and then well, the nominal features, how is like it as a string? Well, can we still use the k-means? Well, and I give you another example. Okay, so here if we have a data set of the employees, and in this data set we have the salary, and then we have the gender, and we have the race, we have the department. Okay, so for this data set, how do we use the k-means to cluster the samples? So think about that. Okay, you may say for the numerical features we can keep them, right? So for salary we just keep that, and for the gender, and we apply the one hot encoder, or we can say, well, if it is true and then that is a male, and if it is false it is female, we can do that. So because anyhow gender is a binary data, so we don't have to worry about the gender too much. Okay, and how about the race? And there are probably a couple of the different races, and then we have to do the one hot encoder. And for the department, IT, business, sales, so we have to do the one hot encoder as well. So, well, using the techniques we have learned from this course, and we can process the data for sure. Okay, so the final data set will be salary as one column, and gender and another column with 1 or 0. And then for each of the race, for each of the possible race, it will be a feature. And for each of the different department, it will be a feature, right? So let's come back to the question. How do we want to use k-means, or can we still use the k-means to cluster this kind of data set? Okay, so well, the point I want to make here is, well, k-means is a clustering algorithm relying on the distance matrix, right? Because we are assigning all the samples to the nearest centroid. So how do we define uh, the nearest centroid? We are measuring the distance. So in the k-means, we are relying on a meaningful distance measure. Okay, it can be Euclidean measure. It could be a Euclidean distance, or Minkowski distance, or Manhattan distance. Whatever distance you want to use, you want to make sure that, well, the distance measure you are using is meaningful. Okay, if we come back to this data set, after doing the data pre-processing, we have already discussed applying the one hot encoder to the race and the department. My question is that distance matrix, for example, Euclidean distance, is that still meaningful when we are trying to measure two samples? Okay, we have already done the one hot encoder, and probably we also want to do a standard scalar, but after doing that, can we still measure the distance of the two samples? Well, is that still valid enough? And that is a question you have to think about. And for this part, for this question, probably I would say it's not that valid anymore because, well, if we have the two workers, they are they're in the same department and they are earning the same salary, and however, they are of different races. And then how do we measure the distance? It can be really hard. So if we cannot come up with a valid distance matrix, then probably k-means is not that useful, or we have to justify the distance measures before we move on and do the k-means. Okay, so very quick review, a very quick sum up. So for the SSE, it can be used to evaluate the quality of the clustering. And remember, we want to do the able method. And for the able method, we will when we are trying to track the drop the drops of the SSE, and we will see at the very first there is a very quick drop, and then after a point, well, the SSE is still dropping, but the drop rate is much slower. Okay, so that the turning point of the k will be the point we want to pick. Okay, well, k-means, remember, k-means does not give us the optimal clustering result. And then when you run the k-means several times with different random seed, and you will get different results. And this is not a big surprise. However, the good thing of the k-means is k-means runs very fast, and usually we consider k-means as a linear time clustering algorithm. And for the the last thing is, for the k-means, it relies on a meaningful distance measurement. And if you don't have that, and then you may have to work on this first before you move on and do the k-means. Okay, so that's it for this lecture, and I will move on and give you another exercise.